When I see a new problem, you know what I do. This is 2905. Find indices with index and value difference number 2. All right. So you are given a 0 indexed integer array nums having length n, an integer index difference, and an integer value difference. Okay, so you're given 3 things. You're given an array called nums. You're given an integer, I guess this is an integer array. You're given an integer index difference, I'm just going to call it ID, and you're given an integer value difference, VD. All right. Your task is to find 2 indices, I and j, both in the range 0 to n minus 1 that satisfy the following condition. The absolute difference between I and j is greater than or equal to index difference. So the reason it's called index difference is a pretty self-explanatory meaning given this context, right? Because the idea is that the values are index difference away from each other, right? So if I select value I have to select a value at index j. Yet if I select a value at index I have to select a value at index j. That's index difference apart. And absolute numbers of I minus numbers of ij is greater than the value difference. So the difference between these two values that are index difference apart is at least value difference. Okay. Return an integer array answer where answer equals ij if there are 2 such indices and answer equals -1 otherwise. Okay, so just find some place where these two conditions are met, and if you can't find any place where that occurs, just return -1. If there are multiple choices for the 2 indices, return any of them. Note, I and j may be equal. So that would only happen if index difference was 0, right? Okay, so let's do this example. So, for example, we have nums equals 5141. Okay, 5141. And we have index difference equals 2 and value difference equals 4. All right, so the answer is 0, 3. Now, let's just first go through what you may think is the answer initially, but we'll quickly realize can't be the answer given that there's multiple constraints, right? So you might be compelled to say, oh, 5, 1, that's the answer. The difference is 4, right? The difference here is 4, so that's the answer, right? Why can't I return 0, 1? Well, the elements have to be at least index difference away. So they have to be at least 2 indices away from each other in order for them to be the answer. So looking at these values alone isn't sufficient in order to determine whether or not, these values meet the conditions, right? So that's why that isn't the answer. And then you might say, okay, well, they have to be at least 2 away. So these 2 are at least 2 away. But the issue is that this is only +1, right? So the difference has to be at least 2, and this is 0 and 2. So the distance is 2, but the value difference isn't correct, right? Because the value difference has to be at least 4, and the value difference between 5 and 4 is just 1, right? And if we look at this next one here, we'd say, okay, how about this? Well, the index difference is 0, 1, 2, 3, so that meets this first condition. And the value difference is 5 minus 1, or 1 minus 5, absolute value is 4, so it meets both of these conditions. So we can return this index and this index, which is 0, 3. All right, simple enough. Do we think that doing another example, this index difference is 0, value difference is 0. So, 0 and 0, the value difference is 0, value difference between 5 minus 5 is 0. So, just showing you that there's a kind of trivial example there. If these values are 0, 1, 2, 3, this is just showing that there's nothing that meets the case, right? Because the index difference has to be 2. So the only elements that are 2 indices away are 1 and 3, and the difference between that is 2, but it has to be at least 4, so there's no solution. All right, let's look at the constraints really quickly. Well, num's length is 10 to the 5. Num's I is 10 to the 9. So if we say n is equal to the num's length, right, we're going to need a solution that's somewhere in the realm of, O of n to O of n log n, right, maybe. All right, so one good thing about this, about looking at the constraints, is it can indicate, what is necessary in order for you to get the answer. Maybe it's faster than this, right? But maybe the solution is even better than O of n log n. But if it's 10 to the 5, right, Leetcode will start giving you time limit exceeded after about 10 to the 6, 10 to the 7 operations. So if you have 10 to the 5, n squared is definitely not going to work because that would result in 10 to the 10. So we're definitely in a situation where if we can get something that's O of n, at the worst case maybe O(n) log n, we're going to pass. So we have to think about that when we're doing this problem, right? That doesn't mean that the solution isn't better, right? The solution could be, constant for all we know, right? But just looking at the constraints and saying, okay, the solution is probably within this realm given the constraints of this problem is always a good idea because it can kind of help you. It's at least some sort of hint, right? Indication about the complexity of the problem. Okay. All right. So how are we going to do this? Well, I'm trying to think about the best way to describe how you're going to approach this problem. Let's start with a general case, right? Let's just say we have elements, I don't know, A, B, C, D, E, F, G, or let's just call them X1, X2, Xi, Xj, just making a very, Xz, I don't know, or X to the N, because N is the last element here. Okay. Let's think about this in terms of, well, if we look at a certain element, right? For example, if we look at x of j, and we were saying, okay, is x of j a part of my answer? Meaning, is this the jth value, right? Is this going to be the jth value that I return, right? Because we return the indexes I and j. Meaning that we return, the jth index of the value and the ith index. So we look at x of j, right? We say, okay, for this j value, what could possibly be a solution for this x of j? Well, it has to be index difference away, right? So the only thing that can be I is there has to be at least index difference, I'm going to call it ID, away. Right, what I'm saying here is the distance has to be at least ID. Right, so x of j, it's going to say, okay, if this is going to be the jth value, well, the thing I can compare it to, the only elements I can compare j to have to be index difference away, right? So let's say that that's this x of I value. So there's a bunch of values in between, So that means I can compare it to any of these values, right? Because these values are index difference away, all right? Now, I could linearly go through and say, okay, I'll compare it to, I'll make this I the value, and I'll look at each one, right? I'll say, okay, it has to be index difference away, so that, let's say x of I is index difference away, and I can compare it to each one. I can say, okay, is it this one? Are they value difference away, right? I subtract x of j from x of 1. I say, is the value difference away? No. To x of 2, I compare those. I say, are they value difference away? No. And so on and so forth, right? Now, that would be an n squared solution, right? Because you have to look at each element, then you'd have to look at everything that's index difference away up into that element, and then, traverse through. Right, so what I can say here is I say, well, I know for sure that I should ignore the elements that aren't index difference away, right? So I kind of have constrained a little bit all the elements I should look at, right? There's no reason to look at the elements in here, compare them to j, because they're not index difference away. All right, and how that relates to this initial problem, for example, is when I look at 5, right, everything has to be 2 elements away. So the only thing I compare it to is things that are 2 elements away, and there's nothing. Then when I look at 1, I can only compare it to things that are 2 elements away. I look 2 elements away, there's nothing. I look at 4, right? And that's why we didn't compare 1 to 5 here and say, oh, 1 to 5, the value difference is 4, so we actually have the answer, right? No, we couldn't do that because we can only compare it to things that are 2 elements away. We kind of filter out the things that are closer than the index difference away in order to ensure that we're not comparing it to something that doesn't meet this, first condition. And then when we look at 4, we say, okay, the only element that's 2 index away is 5. All right, good. We actually have an element that's, index differences away, but the value difference is insufficient. And then when we look at 1, we say, okay, it has to be at least 2 indexes away. So we can look at it 1 compared to 1 and 1 compared to 5. And we say, okay, that's the answer. All right. So that's kind of the first part, right? The first part is a realization that only look only compared to elements xi for xj where I is at least index difference away. And what I'm saying by that is, you only compare this xj value to these x of i's as long as I is at least index difference away, but it could be greater than index difference away, right? But I don't need to look at this area within this gap, right? This gap is unimportant. This index difference away gap, I'm going to not neglect, but I'm going to ignore that because it doesn't meet the first condition. Okay. Now, when we get to this next part, well, right now we're comparing j to all x of j to all the elements within this boundary, right? From the beginning all the way to an element that's index difference away from the current element. All right. Now, we could compare it to each element, but all we really need to do, you think about it, is say, well, how can I explain this? Let's just say we had a group of people, okay? For some reason, I always like to explain these problems as people because for some reason that always adds this relatability, right? Let's say we had a group of people, right? All right, and these people just all have, I don't know, different heights. Okay. And then we introduce this new person. Okay. Now, God damn it. All right, we introduce a new person. Now, if we were trying to find, let's say we're just trying to find someone who's at least, a value difference away from us, right? Nums of I now would be the heights of these people. And I can say, I'm just trying to find someone who's at least, 3 inches difference in height. Now, of course, I could take each person, right? And I could compare them. I say, are you guys the same height? Right? And then compare him to him, then compare him to him, compare him to him, and compare him to him. Okay? That's one way of doing this. Now, if we're talking about at least a difference in height, if it exceeds that, it's okay, right? We don't need to know the person who's closest to us in height, that's greater than our height or less than our height. We just need to find someone who's at least that difference in height. So you really don't need to look at each individual person. You could just say, well, what if I just took these people and sorted them based on their height, right? The only people I would need to compare myself to is the tallest person and the shortest person. Right? Because I'm just trying to find the greatest difference in height. So my greatest difference in height is either going to be with the shortest person or the tallest person, right? Because if I'm shorter than, the guy to my right here, well, then I'll definitely be shorter than the guy to his right because that guy's only taller than him, right? So if I'm just trying to find the maximum difference in values, right, the maximum difference in heights, well, I'm either taller than somebody, so I'm taller than whoever they're shorter than, so it only would increase the difference, right? For any spot, if I put it here, I'd say, well, the difference in height is small here. I'm slightly taller than this guy, and I'm a head shorter than this guy, right? And you might say, okay, well, I need to compare to each value. Well, if I'm just trying to find the maximum value difference to meet this condition, right? Because if one value meets the condition, the maximum one definitely will as well, right? If I'm taller than this guy, then the difference in height can only get greater to this guy's left because people to his left are shorter than him, right? I look at this guy and say, I'm taller than you, and the value difference is X. Well, this green guy is going to say, well, if the value difference between us and X, it can only get larger to my left, right, to this left, because people to this left are only shorter. So what I'm basically trying to say here is I don't need to compare myself to everybody. I just need to look at the tallest person, right, and the shortest person and see which one of those differences is larger. And if that's going to be the best case, right? That's going to be the best case for finding a value difference that's as large as possible to meet this condition, right? Because anything else would only be smaller. Some other elements may still meet the condition, right? There may be that 6-inch height difference that I want between these other characters. But if it's a 6-inch height difference here between me and someone who's taller than me, then there'll definitely be that same height difference for someone who's even taller than them, right? Okay? So all that's to say is when I get here, right, when I'm looking at J, I don't need to compare J, x of J, to all these elements. I only need to compare x of J to the elements that are the smallest and the elements that are the largest, right? If I'm, shorter or taller, I'm in the middle or whatever, if I compare myself to those two, those will be the best places to find the maximum difference, right? Anything in between, right? Anything in between will only be less significant than these two extremes, right? I only need to compare myself to the two extremes of the spectrum, right? Whatever's happening inside of here is kind of a black box, right? Whatever's going on in here is irrelevant because it's only going to get more extreme on the edges, right? That's kind of the point I'm trying to make here, right? When I'm comparing this guy, right, I only need to compare him to the tallest and the shortest. Anything in here is only going to be a smaller value difference than comparing him to the tallest and to the shortest. That's kind of the point that I'm trying to make here. So when we do this problem, when we look at J, as long as we keep track of who the tallest person is and who the shortest person is, then we'll always know who we should compare this value to, and we don't have to compare it to everybody. We just compare it to the tallest and to the shortest, and we keep track of that as we go through the solution. So with that said, what we'll instead do here, and I'll rewrite this problem down. So remember we had nums is 5, 1, 4, 1. And then we'll look at each J values, and we'll keep track of the minimum value and the maximum value. Now, we could look at 5 first, then 1, then 4, but there's really no point because there's nothing to the left to compare it to, right? So when we go through here, we'll keep the index of the minimum I and the maximum I, right? And then we'll say, okay, at the initial, it's just 0, 0. Now, the first person we're going to look at is 4 here because the distance has to be 2. So we say, is 4 what? Is the value difference between 4 and the maximum person and the minimum person at least value difference? No. Then we move on to the next one. The example problem is so small, it's hard to really articulate what's going on here. Then we update min and max. So we say, all right, now we have a new person, right? We have this new person. We have this new person 1. And we say for this new person 1, are you smaller than who I used to think was the smallest person? I used to think 5 was the smallest person, so now there's a person of 1. So maybe the best way of doing this would be to... Now let's just keep doing it like this. And I think when I code it, it'll make more sense. I think these ideas make sense. The actual traversal that you do will make more sense when I actually just write the code. But I think these ideas of, there should be this gap because it should be index difference away, and that we don't have to compare x of J to everybody, only the shortest and the tallest makes sense with the second point here, right? We compare it to 1, though, we would say, oh, well, actually, our smallest is no longer 5. It's actually 1. And our maximum is still 0, right? Because 5 is still the tallest person in this mix. And then I would look at 1 and 5. I'd look at 1 and I'd say, okay, 1, I only have to compare you to the minimum person, which is this person here, and the maximum person, which is this person here. And I'd say, okay, 1 compared to the smallest person, 1, the difference is 0 because 1 minus 1 is 0. 1 compared to the biggest person, which is, the maximum, which is 0. So that's index 0. So that's the element 5. The difference between that is 4. So I return this maximum and this current value, which is 3. So then I return 0, 3. Hopefully that makes a little sense. So I'm starting by air gapping by keeping this kind of trail in between, right? These things are 2 elements away. I'm looking at 3, but I'm only comparing it to the min and maximums up to this point. Okay. And with that said, let's go ahead and just try to code this, and hopefully it'll make more sense when I do it like that. So we want to keep track of who our minimum and maximum elements are, right? Because we don't need to look at everybody when we find a j value and an I value. We just need to look at, you know, who's the shortest person and the tallest person, compare me to them, and that'll get the maximum value difference. And then those will start at index 0. We're going to look at all j values in the range. Well, we don't want to start at the beginning because there's nothing before it to compare it to, right? There's kind of that gap in the beginning. So we start at index difference, right? Because that's the first place where there's an actual I value, right? We don't have, there can never be a j value here because there's no I to the left to compare it to, because there has to be at least two elements. They have to be at least two elements apart. So I should start here when I start making that comparison, right? Index difference all the way to the length of nums. Now we are looking at a new element, right? And we could add it to our list. So we'd say, well, if nums at j minus index difference, that would be I. So I'll say I equals, well, I'm trying to find AI, so AI, not AI. Ni, right? I value, not AI. Nums index difference. So we say if nums of j of index difference is less than the minimum, that means we found a new minimum at j minus index difference. We did the same thing for the other side, right? If we're saying, okay, so if whoever I thought was the shortest person, if the new person, remember with that air gap, if the new I value I'm encountering is less than that person, well, then that's my new smallest person. And I can do the same thing for my new tallest person. If it's greater than the maximum, well, now I have a new maximum value. Right? Because I'm only trying to keep track of the minimum and the maximum. Everything in between, I don't care. So if I just keep track of those two, I'll always have the greatest possible difference that I can get. And then I'll just say, well, okay, if the smallest person, right, which is at least index difference away, because that's how I set this up. I made sure there was a gap in between. If the absolute value of the smallest person, that's at least index difference away, minus the current person that I'm looking at, the current number at index j, if that difference is greater than or equal to value difference, then I'll return that minimum difference and the current index. That minimum index I and the current index j. And I'll do the same thing for the other thing. If the difference between the maximum and me is greater than value difference, then I'll return the maximum in j. And if I go through the whole problem and I never find anything, I just return -1, -1. Pending, 1, 2, 3. I wish someone would try me. All right, so what is the, no, I don't want Leetcode. Huh. What'd I do wrong here, guys? How strange. I don't even know what I did wrong here. So weird. All right, so I assume my minimum and maximum are 0 in the beginning. I look at j. I start at index difference away. So if nums j minus index difference is less than this, then that's my new minimum. Oh, I'm an idiot. Why? It's the comparison. Wait, no. Not the minimum. Yeah, the minimum person. Right? Not just the value, the actual person at that value, right? That's just the thing I get confused about is MI that's the minimum index. Nums of MI is the actual value at that index, right? So if the value at the new thing I'm looking at is less than the value of what I thought was the minimum value, then I do that. All right, it's funny that this still worked. False positive kind of dealio. All right. what is the time? Okay, so let's say n is length of nums. All right, well, for, I think space is the easiest. Well, they're kind of both easy. For space, I just create these two variables, and then I update them accordingly. And then I return, something of size 2. So regardless of the size of nums, if nums is 10 elements or a million elements, all I do is create these two variables and update them accordingly. So that's constant space. All right. For time, well, what do I do here? Well, I look at everything from index difference to nums. Right, so I look at all n elements minus index difference elements, and then I just do constant operations to check, right? I do 4 constant things, right? 4 constant comparisons. I compare these two values, I compare these two values, I compare this, and I update values accordingly. So for n minus index difference elements, it's just called n elements, I do 4 constant things. That's 4 n constant, big O of n. Doesn't get much better than that. Yeah, maybe you had a login algorithm, but I don't know how you're going to do that here. All right. Later, players.